After studying it, the ballistic pendulum is not so hard to understand. You break a complex motion into two pieces. You do conservation of momentum as the ball hits the target, and then conservation of energy as the ball and target together rise to a high point. And at that point it becomes a simple kinetic energy original equals potential energy final, MGHF. But here's a kind of tricky question. Where is the object at the end? Is it here? Or is it here? Or is it here? Or is it here? In fact, it's in all of those places. We've actually been making an assumption all year that we can act as if objects are point particles, that they have a defined location, that a person flying through the air is at 0,63. Well, of course they're not. Each part of their body is in a slightly different location. The soda can, it has a whole range of y coordinates and a whole range of x coordinates. So why have we been able to act as if everything's a point? Well, up till now, most things have been like this soda can. They've been uniform and they haven't had any sort of odd shapes. This is very different. It's got a lot of mass at this end where the ball and target are, tapering off to not that much as you go up to the pivot. So we have to start thinking about where is the mass of an object located. In reality, it's distributed throughout the object. But it's helpful to find an average location for that mass, where if you averaged up all the weight and position of everything in the object, you could say at this point is as if all the mass was there. And we call that point the center of mass. There's a center of mass in each dimension. For this soda can, the center of mass in the y dimension, we would average up all the mass along the y. In the x dimension, we'd average up all the mass along the x. And we'd find that the center of mass in both dimensions for the soda can is right in the middle. That's not going to be the case here. Although what's interesting is that this is pretty much a linear object, so we only really have to think of one dimension. We can call this the x dimension. We'll go through the equations for calculating center of mass later in the year as we study rotation. But for now, here's a trick for finding where the center of mass is. If I have an object and I hang it, the center of mass is always going to go as low as it can. This is on average where the mass is, and if you have mass higher than it is, if you give something potential energy and release it, that energy will transform into kinetic, and eventually it will fall as low as it can go. So the object will always be as low as it can go, and that means the center of mass will be as low as it can go. So let's take our pendulum, we'll release it, and we'll find out where its center of mass is. If I hang it this way, it's pretty obvious that it's going to hang straight down. And that means the center of mass is along this center line. That's something we could have predicted. But what's interesting is we can locate it precisely if we hang it from a different point. Then there'll be another line that goes straight down, and where that line intersects with the center line, that's where the center of mass will be. Fortunately, the people who built this ballistic pendulum, Senko, they made this easy to do. They wanted you to get the center of mass, so they put a hook on the side of the pendulum. So you can see it's hanging at a particular angle. And it's doing that so that the center of mass is directly below the string. We can locate it precisely. I don't know how well you're going to be able to see this, by hanging another weight straight in front. And where the line of this weight intersects the center line of the pendulum, that's where the center of mass is. So in class we marked it with an X. The lab procedure Senko wrote for using this pendulum has you finding how far above the base that x is when it's down low, how far it is when it's up high. And that's how you're calculating potential energy. For a link to that procedure, see the description in this video. We'll use the idea of center of mass quite a bit in our rotational unit. But this was the first time we ever had to think of a center of mass that wasn't directly in the middle, and it was a good time to start talking about the idea. The center of mass is the average position of mass in each dimension.